Okay, so let's get started. I brought a different DNA today. That old one seems to be having a lot of calibration issues. So I'll speak about that also towards the end of the lecture today. Somebody just keep an eye on the time and like ping me around 12:30. We'll finish by 12:45. So this is also a 4-port network analyzer. As you can see, again, there's like this faint blue light here. And that, again, this tells you which port is actually sourcing the power. Of course, that is directly connected to the measurement which is displayed, which you have chosen. And the rest of the features are the same. This is a newer model, so where the different menus are there, they have changed a little bit. But as always, the things you have to set is, I'm going to shift to the VNA display. So the remote people might not have the greatest of view because of the video contrast of the background image. But so again, just to remind you, typically you start by setting the frequency range, start frequency, stop frequency, set up the sweep. Right now it's set to 201 points. You can set the power. This is something we didn't discuss yesterday at all, but the amount of power that is coming out of the port can be set. And usually there is a range of powers you can set. It can go, let's see what is the minimum power here. Okay, this one allows me to go to minus 100 is probably the minimum. Yeah, and plus 10, plus 15. Okay, and plus 20 dBm. This will vary from model to model and the exact features one has set. For linear systems, this power is actually of no consequence because their response doesn't depend on the amount of power. What, of course, does depend from the perspective of the measurement is the signal to noise ratio again, right? If you measure the same quantity with more power, you have more signal. So when you are doing measurements of linear systems, which most of the things we'll be looking at are, in fact, all of them are linear systems, you should use the maximum power possible or the recommended power range. Now, sometimes the accuracy of the instrument itself might change with respect to the power range. And this is again because different powers levels means that something inside is changing, and that can affect the signal to noise ratio a little bit. Usually for typical measurements where you're not expecting a huge change in power from input to output, something around 0 dBm is a good number to work with. That's usually well within the maximum power the system can put out. And this is the what? So 20 dBm. Okay. I guess I have not introduced this this term so far. So this is not 0 dB. You see, it says 0 dB small m. Okay. This is an absolute unit defined in a relative way. This does not mean equal. So what it means, the m here refers to 1 milliwatt. That's the reference power. But this 0 dBm means it's an absolute, it's 1 milliwatt. 10 dBm would be 10 milliwatt. minus 10 dBm would be 1/10 of a milliwatt. Okay. So this is not dB, it's dBm. Everything else we have been talking about. So the y-axis here, which is measuring the transmission in dB, that's dB. So that's just a ratio. Okay. So when I was saying earlier that the response of a linear circuit does not depend on power, it means that the ratio is always going to be the same, irrespective of how much power you put in. Okay. This is not true for nonlinear devices, which we'll be covering towards the end of the course. So often there is a specific range of power you have to use in order for the system to work properly. And if you are working with amplifiers, where the output power is going to be much larger than the input power, then also you have to be careful about how much power you choose here, because you have to make sure that the output of the amplifier can handle that much power. Usually they get saturated. It's like you remember saturation from op amps. Right? If you put in too much signal, then the output cannot go beyond the rail voltage. So similarly, microwave frequency amplifiers also have a parameter which tells you what is the maximum output power it can get, what is the maximum. So for like, there are two numbers typically. One is absolute maximum ratings beyond which you will cause damage. And the other one is the range where it's linear, which basically means that if you double the power, you're going to get double the power at the output as well. So the gain remains constant. Okay. So we will set this to 0 dBm. And let me get rid of the memory part. And let's go back and quickly go through the coaxial cable measurements we were looking at yesterday. And then we'll move on to the other devices. Okay. So I'm using port 1s and 2. And again, I've connected a 12-inch coaxial cable. Let me auto scale this. And now you see something which is actually what should have been yesterday. The numbers yesterday were just all over the place. Okay, so this is transmission measured from S12. So that means the power is being sourced on 2 and it's being measured on 1. And it starts close to so this range was also set, the frequency range is set from 10 megahertz to 20 gigahertz. This one has a slightly different range. This goes down to about 9 kilohertz. You can even set that if you want. Let's go to 9. Anyway, that's just a few points right at the beginning, so you're not really going to see it. And what you expect to see is very, very low attenuation at very low frequencies, because the loss in these transmission line is often frequency dependent, which is what you're seeing here. And then, slowly it increases. And at about 20 gigahertz, we have about 1.5 dB of loss. Okay. Now, this 1.5 dB, what you're measuring as transmission, could be due to two factors. One, that there is actually absorption in the transmission line. So this coaxial cable, which means the power is actually getting absorbed inside the cable as it's traveling, which, it's not a lossless transmission line. But it could also be due to reflection. Okay. So in order to know which one is that, you have to look at the reflection. So if at 20 gigahertz, the reflection is not very high, because 1 dB is a small number, but it's not insignificant. Remember, 3 dB is about a factor of 2 loss in power. So the kind of problems we were having yesterday, let's verify that. So I'm going to put this trace into memory. And I'm going to display data and memory. And I will shift to S21. Okay. So now S12 and S21 look similar. Of course, the traces are not exactly lining on top of each other. And this is basically due to these small inaccuracies in the measurement instrument itself. This is always going to be the case. Okay. You have to worry about the kind of mismatch we saw yesterday. That was just something seriously wrong. They're both coming from the same problem, except that there it was just horribly miscalibrated. And this is because the electronics inside has to be calibrated to know what power level corresponds to what. So this is a procedure which needs to happen. And usually, with factory setting, it comes with a default thing, but that instrument is quite old and has not been calibrated in quite a lot of time. So you're talked about very small mismatches. That's fine. This doesn't mean that there's something unphysical going on, because otherwise a passive circuit showing S21 different than S12 means there's something seriously wrong with that device or with the instrument. Okay. So now let's look at the reflection. So I'm going to get rid of the memory. So I look at reflection from port 1, auto scale. And here you see that, again, at low frequencies, the reflection is close to -30 here. And then there seems to be some frequency range where it suddenly gets worse. Again, this is slightly unexpected behavior. Maybe this instrument is also not in its most optimal state, but this is quite reasonable. Because then it comes back again down to this -30 level and stays there most of the way. And then even all the way up to 20 gigahertz, you have something like -20, -18. So which means that this is only reflecting at the most 1% or a couple of percent of power. So that cannot explain the 1.5 dB of power we saw less coming into the other port. So that is basically due to the losses in the medium. So in general, for a lossy medium, your incident power should be equal to the absorbed power plus the transmitted power and the reflected power, right? So everything has to add up. For a lossless network, of course, what's going in has to come out from somewhere. So either from the reflection or from the transmission, just in the case of a two-port scenario. Okay. Now, let me put this to memory and compare this with the reflection on the other port. And again, this looks fairly similar. There are small mismatches. The same trend at around a few gigahertz where it suddenly jumps up to -20 seems to be there. So it's something, again, related to the calibration or the electronics of this. So in fact, I'm going to just do a test here to make sure that this is not related to the cable, but something with the electronics. So I'm going to remove this. I'm going to put a 50 ohm termination. So this is now just a one-port measurement. Okay. So this looks much better. So it's not something internal to the network analyzer, at least on this particular port. So this is 50 ohm, right? So this should be absorbing everything. So should this cable be, because it's a 50 ohm transmission line, which is just delivering the power to the other side, which is also matched. So from the point of view of the network analyzer's port 2, there should not have been much of a difference. So there is clearly something different with the cable. Let's compare this. I'll put this to memory now. And I will change this to port 1. Okay, so even port 1 looks fine, right? So it's maybe something to do with this cable. We'll try another one, but I want to try one other thing. I'm going to retain a one-port measurement, but I'm going to take this 50 ohm and put it at the end of this cable. Okay. But for that, I need to introduce another adapter because the genders don't match. And that itself can have a problem if it's not good. Let's see if this changes the. So you see that once I connected the cable and put the 50 ohm on the other side, it's not the same as what we were seeing before, but you see there's an overall slightly degradation in performance. There's slightly more reflection. And that's probably because the cable's connector itself is a reflection point, or the cable's impedance might not be as close to 50 ohms as possible. Again, right now we are nitpicking mostly to understand these differences. This is perfectly fine as a cable. Just to verify this, I'm going to connect this to the other port as well. Move this to memory. So the S22 looks fine. Finally, reconnect this. Let's gone back to the way it was. Let me put this to memory and compare it with a different cable. Just to see. This is also a 12-inch cable. It just seems to be something to do with these cables, that they have slightly poor reflection in this frequency range. But again, we're talking about slightly more than 1% reflection. So it's not a bad, like a cable which cannot be used. They recently put this connector, so the thing was little loose. So this connector here, these big ones which you're seeing, they're actually called N-type connectors. And then there is a adapter here which we have put on it to convert it into this SMA compatible. For some reason, they still use these big N-type connectors, which normally are used for low frequencies, but if made properly, they can work up to fairly high frequencies as well. These are more industrial sort of connectors, bigger and rigid and robust. Okay, so that's the cable. So this now makes sense. So the reflection is okay. The transmission is the same on both directions as we expect. And the reflection, this particular feature here seems to be a property of the device itself, so the cable itself. So now let's move on to the splitter, which we were discussing yesterday. So for the remote guys, there's the splitter. It's a 3-port device, and its main purpose is to send in power in one end, and it should split it equally to both sides. So yesterday we saw again weird things. So let's verify this again. Like yesterday, I'm going to terminate the port which I'm not measuring right now. But we will also, since this is a 4-port device, we can actually connect all 3 ports at the same time as well. So the source port is 2, and that is connected to the common port of the splitter, which is labeled S on this on the device. And one of the ports is terminated with the 50 ohms. So that's the matched flow termination. The other one is connected to port 1. And right now we are measuring S22. Okay. So it's measuring reflection on the common port of the splitter. Let me get rid of the memory part. I'll just save this. So what you see here is that, again, remember the range is going from 9 megahertz to 20 gigahertz. The device is rated from 2 to 10. Okay. So at very low frequencies, it has about minus 10 dB of reflection, which is about 10% reflection in power, which is not great. But at around 2 gigahertz, which is the special, it starts to drop. And then it's nicely absorbing here. And then it comes up here a little, is a little bad. And then around here. Then after about 10 or 11, it starts to get quite bad again. Right? So anyway, we should not be looking beyond this. So let me actually stop this frequency sweep. Let's set it to the range 2 gigahertz to 10 gigahertz. So this is what we expect the splitter to be doing, right? This input port should not be reflecting much power. It should be absorbing all the power at the input port. Absorbing meaning here, allowing the signal to go through. It's not dissipating it inside the splitter or anything like that. Okay. So that's what we expect. And because this is again a matched 50 ohm device. So we expect this to happen. It's not excellent at the ends. As I said, usually minus 20 dB is considered as the sort of the reference point. But out at the wings, it gets close to minus 10. But that means you lose a little bit more power to this. Now let's look at the transmission. So since I've connected the common port, the source port to port number 2, so the common port, and the output to port number 1, which measurement should I choose to look at the transmission? S12, because we are going into 1 from 2. You auto scale here again. And now you see that this mean power, of course, it's varying. There are some ripples, but look at the scale. It's only going from minus 5.4 to ideally, it should be around minus 3 dB. But yesterday, as I was saying, there is always going to be some extra loss, both due to components inside the splitter and now partly due to this cable. Okay. We know this cable gives about 1.5 dB of loss at 20 gigahertz. At 10 gigahertz, it was maybe about half of that. So it's not an insignificant amount, but it still cannot be completely ignored. And this is actually where, for example, there's no other way for me to connect this to the instrument without using some cable. Now, I could have used a better quality cable which has lower loss. But this is one of the things you can actually get rid of by doing a calibration, which will remove the effect of this cable. Okay, I'll come to that towards the end of this lecture on what exactly goes on there. Okay. So it's seems to roughly have 1 dB extra of loss. And that is a number which would be typically given in the data sheet. It will say insertion loss. And sometimes it might include the 3 dB it is supposed to do, and sometimes it might take out the 3 dB. It will say, so it'll either say 4.5 dB insertion loss, or it might say 1.5 dB insertion loss on top of the 3 dB which is expected. Okay. So so this is the transmission, and this is doing what it's supposed to do. Now, even though I asked you which port to measure, because it's a passive device, we know it should be reciprocal. So it should not really matter whether I measure S12 or S21, and they are mostly the same. Okay. So again, I want to emphasize that S12 and S21 are actually two independent parameters of a network. An ideal passive network, which is reciprocal, will have those two terms to be equal. But when you use an instrument like a network analyzer to measure it, it's not the same as it's not actually measuring the same thing. Okay, it's actually measuring two different things. That's why you have a difference here. Maybe I'm sorry? No, this is not due to the loss in the system. This is due to the calibration of the instruments. Like, it cannot measure things more accurately beyond a certain path. So there could be slight path differences, there could be slight gain differences, which give rise to a slightly different response. What I'm trying to let me see. What I'm trying to say is that, again, there's nothing unphysical going on here. It's not that when it's carrying out this measurement, it's doing the same thing but getting different results. That's not what is happening, because the two measurements are indeed different. When I'm measuring S21, I'm sourcing it from port 1. And when I'm measuring S21, I'm sourcing it from port 2. This itself, because internally there is a switch which is going to switch the power. If that switch is not perfect, it could be sending slightly different powers to the two things. Sorry, Lakshay, Jay is trying to call me. Can you just call him back and tell him, unless it's a lab emergency?
Sir, people can take the input power at a specific point, right? In a specific input question. Now we are sending, when you are measuring S21, we are sending the input from different.
Yeah, but this is not a filter, it's a splitter. But even if it's a passive device, it doesn't care where you send the power in, right? So depending on where you send the power in, it will respond according to its design. But because this is a passive network, it should be reciprocal, which means whether you measure it from one way or the other, it should be the same. Okay.
Now you are sending power in the output.
That's what I'm saying, that the definition of input and output port is just a nomenclature for this device of how it is used in a standard fashion. Okay. It will behave, it will give you some response. And in fact, that's what we're going to see next. We can actually look at all the combinations. So I will connect the third port also with a cable, and we'll see what all the combinations are and whether they make sense or not. Okay. So if there is a path in one direction, there is a path in the other direction. And if it's a passive reciprocal device, they will give you the same result ideally. Okay. So just to come back to this point, what I was saying, yeah.
So interference depends on the length of the coil.
The what?
The length of the coil. The interference.
This interference pattern could depend on the length of the cable. It could depend on and some internal path length in the system. It could also depend on the internal path lengths inside the device as well. But this is something we can check right away. Let's increase the length of this cable by adding an extra cable there.
When changing the direction of the path length, path given is going to change. So
that can happen if the internal electronics is slightly mismatched. I see what you're saying, that this why this ripple pattern seems to have changed its period. Right? Sorry, Panya, you really need to speak up. Like you're sitting right here and I can't hear what you're saying.
I was saying via cloud, when you get it as an interference pattern.
As an interference pattern. Okay, I'll just answer that. Give me a second. Let me switch back to the other measurement so that we can compare it more carefully. So you see, this ripple pattern doesn't seem to have changed. But what has changed is the overall transmission has come down. That's just because of the longer cable. Okay. So this is something to do with the frequency response of the device itself. So what he's referring to is an interference pattern, is that usually when you have any cable in the system, there will be some reflection at the two ends. And that means that that can set up a standing wave, a weak standing wave. So there will be frequencies where it will be slightly, you'll get constructive interference and slightly destructive interference. And that will give rise to small changes in reflected power or transmitted power, depending on the exact situation. So if you change the length of that cable, then the two reflection points change. So then the period over which you will get the constructive and destructive interference will change. This typically happens when you take long cables. If you even just look at a coaxial cable of different lengths and you look at the patterns in the reflected signal, then you will see that they will get closer and closer as you increase the length of the cable. So the interference, because now we are having multiple reflections, so it's happening that way. Let me put this back. So just to finish that thought, S21 and S12 are really two different measurements being carried out by this instrument. And that can give you different results because of the calibration itself. So let's try one last thing. Let's measure the same quantity from the instrument, but invert the connections so that it effectively measures the opposite quantity. Have you understood what I'm saying? So I'm not going to change the source. So right now it's set up to measure S21. So power is being sourced on port 2. It's going to the common port of the splitter. And from one of the ports of the splitter, it's going to port 1 of the network analyzer. And that's the path it's measuring, right? What I was saying is that if I now change the measurement to S21, then the sourcing of the power is from port 1 and the receiving is from port 2. So if there is something different going on in the network analyzer, that can give rise to small changes in this thing. What now I'm saying, I will go back to S12, but I will just interchange these connections here so that the common port is connected to port 1 of the network analyzer, and the transmitted port is connected to port 2 of the network analyzer. So the instrument is still measuring the same quantity, but I have flipped the connections so that it now effectively is measuring the transmission in the opposite direction. And again, you see there is some slight difference over here. Okay, so let me put this to memory, switch it back. What did Jay want?
I think you wanted to verify that is the correct word.
What?
I think some
Settings.
yeah. That is what you are talking about.
Let's switch measurement to S21. So it actually matches, right? So this is really something to do with the going on with the device itself, which is giving you these slight changes. So we verified it's not so much to do with the internal electronics. There's some changes. It's not exactly the same. Okay. Some non-ideality in this device. Now to finish up this thing, let me connect the third port as well. And then we'll see how this device actually looks. Basically, we can look at all the scattering parameters. So just to now look at this immediate comparison, all I have done is I've removed the 50 ohm termination from the second output port and connected to the vector network analyzer. As I explained yesterday, this is equivalent to terminating it with 50 ohms because the network analyzer always ensures that all ports are seeing a 50 ohm impedance. Otherwise, these measurements will not make any sense. The curve looks almost the same, some slight mismatches. This is because this is not exactly the same situation as before because the 50 ohm termination location is now displaced by a cable. So the cable could have slight reflections and that will affect the overall transmission a little bit. Okay. So the reason I'm sort of over exaggerating these points is that you should not get bothered by these things. This will take some time getting used to when you're actually using these kind of measurements in the lab. So you need to develop an intuition for what weird things on the screen one should worry about and what one should not worry about. Okay. This kind of stuff will always happen. And this is mostly because the point of nothing is perfect in this world, right? In this microwave regime, you can never have this idealized behavior. So you just need to know how non-ideal things can get before you start worrying about it. Okay. So now let's look at it, this device completely. So let me get rid of the memory again. So right now I've connected the common port of the splitter to port 2 and the two output ports to port 1 and 3. That's the configuration. Let's start looking by reflection on all the ports. So this is on port 1. So this is one of the output ports of the splitter. And it looks to be quite decent. Most of it is below -15, maybe a little bit below -20. And this is again 2 to 10 gigahertz range, which is the spec operating range of this instrument. Let me just increase the number of points. Sometimes I'm seeing resolution issues here. So I've now increased it from 200 to 1000 points. So that's S11. I will put this to memory. And now we'll shift to S22, which is the common port. Okay. So this one is slightly worse, which is kind of strange compared to the other one. But we saw that earlier also that it was close to -10 at the edges, and then it got better in the middle. Sorry, just 1 second. My iPad seems to be running out of power. All right, I'm taking a risk and turning something off. Okay. Okay, the remote guys, you should have received the video feedback again. Okay, so that's S22, which is the deflection on the common port. And then let's go to S33 and S33, which is the reflection on the second output port, looks similar to the reflection on the first output port, which is what we had put to memory. So the orange trace. Okay, so that's expected because this device should be reasonably symmetric on either side. So we have looked at reflection on all three ports, and it's verifying that it's a matched 50 ohm device. It's absorbing the power on all the three ports. Now, come back to data. We'll now start looking at the transmission in the normal direction, which means to the output from the input. So the input port is 2 and the output ports are 1. So we'll source from 2 and measure at the output at 1 and then 3. Not loss. I mean, that's the reflection. The reflection is worse in this. It's just something design of the. Ideally speaking, it should be the same, but the output ports and the input ports are not exactly the same in terms of the structure of the circuit. Okay. So later on, when we actually study this particular splitter, which is a type called Wilkinson divider, you will see how it's actually constructed inside, like what are the input transmission line and output transmission lines. And again, many of these rely on some kind of interference phenomena. And that again happens ideally at some frequency. So there'll be an ideal frequency of operation, and the operation will get progressively worse as you go away from that ideal frequency, like we saw for impedance matching circuit or impedance transformer circuit, right? The transformer is defined at one frequency, and then it gets worse as we go along. So similarly, these things also have that. So it just happens that this particular splitter has a response like this. We will compare this with another type of splitter just immediately after this. How are we doing on time? Okay. So now let's look at the transmission to one of the ports. So the destination is 1 and the source is 2. So I'll measure S12. We auto scale that. And so we saw this earlier. It's roughly 4 dB and it goes up to something like 4.8 dB at 10 gigahertz. I will put this to memory. And now I'll compare this with the second output port, which is now 3. So I need to measure S13. So source, S32. Because the source is still, and see, it's slightly different, but mostly it's the same. So it's doing roughly equal power over here. So in terms of the regular operation, these are only the 5 important numbers, right? Reflection from all ports telling you that it's matched, and then transmission to the 2 output ports. Now we can look at the reverse aspect. So this was S32, so I can look at S23. And because we know that this is a reciprocal device, we expect it to be the same. Okay. We will discuss what it means when you operate in reverse in just a second. But what it's telling you is that if I put in power at one of the output ports, half of that power, same function, comes to the common port, the original source port. Okay, so it's the same. So you had one input, 2 outputs. If you send in power from the input, 3 dB of power goes this way, 3 dB of power goes that way. Right now, what we're saying, I'm putting power here. It tells me, and I should expect that 3 dB of power will come here because it's a reciprocal system. We have not yet seen what happens to the rest of the power. Okay, we know that it's not reflecting because we have checked that the reflection on each of the port is good, like it's low reflection, which means it's absorbing power. So that power must be going somewhere. We will check that in just a second. So again, repeating, we send the signal into the splitter, 3 dB comes out of one of the output ports. If you send power from that output port, 3 dB power will come to the input port, and that's because it's reciprocal. Okay. Same way, if I now change the source port to the other output port, which is going to be 1, so then I have to look at S21, and that also, as expected, looks the same. So if you send in power from any of the output ports, 3 dB less power will reach the common input port. Now we have to check what is happening if it is between the output ports. So right now I'm sourcing from port 1 of the network analyzer, and it's going to one of the output ports. I will now measure what is coming out of the other output port. Okay, so that is port 3. So I'll measure S31. Okay, it's not visible here. Let me auto scale it. So the orange trace is the reference trace for one of the 3 dB transmission levels, right? But what you are seeing here is that if I look at the transmission from one output port to another output port, it's actually very small transmission. I mean, there is finite, it's about minus 20 dB, but this is only 1%, right? As opposed to 50% over there. Okay. This is again not unphysical, right? This is not violated because these two combinations of port, we are just looking at it for the first time. But what does this mean? I send in power from one of the output ports. 50% of that power comes to the common port. No power is coming. So, I mean, it's no power in the ideal sense is coming to the other output port. So, and we know that it's not reflecting. So what's the only interpretation of what's happening to this power? Getting absorbed? Anybody else? Is there any other possibility? No. We just looked at S11. S11 is good. It's only reflecting about 1% of the power. Where is the rest of the almost 50% power is missing, right? So Lakshay says is getting absorbed. Is there any other possibility? Let me draw this here. I'm sending power from this port. I know that no power is getting reflected. I'm idealizing the responses you're seeing. I know that 50% power is going here. So this is 0. This is 0. This is 50%. Is anything left? So the only thing that can happen is that this power has to be disappearing somewhere inside the device. So what Lakshay is saying is correct. It's getting absorbed, and that we will understand when we actually look at the device itself. Like there's actually a resistor inside the device, which will absorb a power when used in this direction. Okay, but there's something subtle to it. I'll mention it in just a second, but I will not go into the explanation of that. So this is again a characteristic feature of this kind of a device. The fact that no power goes between the two outputs means that this is isolated. Again, in the ideal sense, it's mostly isolated, very low power. So port 1 and port 2 are isolated in this manner. So what's the use of this this kind of a device if I'm using it in the opposite direction. Right? This direction is simple. The purpose of this device is to put power in and get 2 copies of the signal, 50% on each arm, plus whatever insertion losses. But in the reverse direction, if I send in power here, nothing goes here, 50% power comes here. So that's kind of a strange thing. It's not really useful in that sense. But if you send in power to both ports, then the subtle thing happens. If these 2 signals are actually just completely independent signals, imagine this is a signal at frequency omega 1, this is a signal at frequency omega 2, then what will happen is 50% of this will come here and 50% of this will also come. So this works as a combiner as well, with the caveat that you always end up losing half the power. So half the power in the sense of what you started with. If this was power P1, you will only get P1 over 2 plus P2 over 2 on this port. The rest of the thing will dissipate inside. But if you don't care about that aspect, this is one way of combining 2 signals into one common transmission line. Why would you want to do that? Because you might want to send multiple signals to the same device, which is coming here. And you have 2 sources producing omega 1 and omega 2. And this is one way of combining. But this is always going to result in that 3 dB loss or 50% loss of power. That's a feature of this particular type of device. However, the catch here is, or there is one special mode, if both of these signals are at the same frequency. The reason I'm talking about same frequency is that earlier I said if these 2 are independent signals, what I mean is that there's absolutely no phase relationship between the 2. So when the frequencies are different, you cannot define a fixed phase relationship between them. Okay. But if the frequencies are the same, then you can talk about, it could still be completely random, the phases could be random, but you could then have a situation where you have a precise phase relationship between the 2 signals. In that case, if these 2 are exactly in phase, then the total power coming out will actually not have that loss. If this was A sine omega t plus phi 1, and this one was B sine omega t plus phi 1, say phi 1, then the output will be A plus B. In fact, the amplitudes will add. This is because the functioning, the actual functioning of this device in this reverse direction is that on this port, it gives you the sum of the voltages on port 1 and 2. And the difference of voltages of 1 and 2 gets dissipated inside this hidden resistor. Okay, this is something we will derive later on when we actually study this device in detail. So that's why if you now consider this as the operation of the device, that on ports 1 and 2, if you put 2 signals, the sum comes on the S port. In fact, that's why this port is labeled S. It stands for sum. Sum comes out here, then you know, and the difference comes out on the internal port, which is actually basically a hidden 50 ohm port inside. Then you know that why, if I put 2 completely independent signals, on an average, I'm going to get half the signal on the sum port and half the signal on the difference port. And you only have access to the sum port. There are 4-port versions of this device as well, where the 4th port is actually outside and you can look at this. So this is something we'll see later on. So how does one actually, one way of testing this is that if I took a signal, if I took 2 of these devices, so I start with a splitter and I take that and put it back into another splitter in reverse. These two signals are at the same frequency and have a precise phase relationship between them. So if that is sent in here, you will recover that signal back from this side. Okay. So if this is amplitude V, remember it's half power, so the voltage here will be V over root 2. This will be V over root 2. And this again, because it's sum, it's going to be V back here. So if the two splitters are identical, then this would happen. So this is one way of putting signals in with the precise phase relationship between the two, but there are other ways of doing that. So now I said something which I had not mentioned earlier, though I might have mentioned briefly. I'm now talking about the phase relationship between what is coming at the output. Right? Can we check that? Yes, we can, because the network analyzer allows us to measure phase. So far, we have only been looking at magnitudes. So now let's look at the phase as well. So I will go back to measuring the standard direction, which is input coming from port 2 and output is either port 1 or port 3. So that's first, let's look at S12 auto scale. This is your magnitude. Now I'm going to go and look at phase here. Can everybody see the screen? What's happening here? Okay. So since yesterday we were having this weird problems, let me just do one other thing. I'm just going to show you what happens to just a transmission line when it comes to phase. I'm just going to disconnect the splitter. Let me get rid of the memory. This is S21. So right now I only have a coaxial cable connected between ports 1 and 2. And this is S21. And you see that the phase is running from some value and it keeps decreasing and then it jumps back. So this jumping back is just the fact that you're restricting the phase measurement between plus and minus 180 degrees. So total 360 degrees. That's the standard reference. There are probably some measurements here in microwave office also. I think I mentioned that there's this unwrap phase thing, which allows you to keep it in the same direction. But that's what is going on here. And what you're seeing is just a linear phase increase as a function of frequency. Yesterday, I had mentioned this. Remember that it takes a finite time from one to another because of the length of the transmission line. So the phase which is going to accumulate is going to be proportional to delta t, which is proportional to the length and frequency. So omega delta t is how the phase changes. So omega is changing linearly along the x-axis. So the phase is changing linearly along the y-axis and then wrapping around over this. So this is what you expect for a cable's phase to look like. Okay. Now, sometimes, because this is a trivial phase, right? This is something just because of the length of the transmission line. And we were seeing something exactly the same when we connected the splitter because that length is still in the picture. So this kind of very fast and the longer the cable, the sharper the slope of this phase change would be because delta t will be larger. So on that screen, you will get many more things packed into the same length. So there is a way, because it's a trivial thing, there's a way to just unentangle this trivial phase difference or phase evolution, so that you can actually see the phase response of the device you're interested in, which is not the coaxial cable. Okay. So that part is now, let's see if I can find it here. So you see this thing called electrical delay. This allows you to dial in a number which will then basically trivially cancel out this particular feature, because it knows what the frequency is. Essentially, you're dialing in the length or the delta t. So you can enter them in both directions. So you go to the delay time and you enter a value of, say, 1 nanosecond. So it has now partially compensated it, because it's now sort of introduced a negative delay internally, just as a pure calculation thing, right? And so this is not enough. So I need to go a little bit higher, but this is too high now. It has overcompensated. So now you see the phase is going in the opposite direction. So I have to go somewhere in between these two numbers. So it's now almost flat, but I need to increase it more, a little bit too much. Come back 1.5, 3, 1.54, 1.56. And now it looks nice and flat. Okay, all I have done. Sorry, louder. All the instrument is doing is that. So first I explained that this phase evolution is a trivial response of the cable. Okay, it's just increasing as a function of frequency because of the time difference it takes to go signal from go to 1. Remember, we're measuring S to 1, right? So the phase when it started versus the phase when it received at the other port, it's going to accumulate an extra phase because of the time difference. And that phase accumulation will be more if you're at higher frequencies. So omega into delta t is basically the phase accumulation. And omega is varying linearly across the x-axis. So you saw this linear thing. So let me actually put this back to reset this so that you can see what we were having about it. I'm just doing a transformation inside to get rid of this phase change, because this phase change is not giving me any information. Whereas the device I'm trying to study could have some other interesting phase relationship, which I might need to verify. So for example, we had talked about LC resonators in one of the early classes. So that has this 180-degree phase shift as you go through resonance. If I put a resonator at the end of a cable and do a measurement like this, I'm going to be completely obscured by this trivial phase shift. So by entering this number here, I'm just telling the instrument that for basically subtract out the effect of this length of coaxial cable. Ideal coaxial cable. It cannot do anything. This will not affect the losses or anything in the cable. So that
it can do this because the velocity is constant.
Yes, of course, of course.
But when we are making the system it would be frequency dependent. Okay.
Well, in most cases, you don't expect the velocity to be frequency dependent. You mostly don't study dispersive systems. But remember that we are only cancelling out the effect of a coaxial cable. A coaxial cable should not be dispersive. If your actual device is dispersive, that you will see.
Let's say I built up a system. So what I will do is I will not connect it to the device, but I just connect it directly to see what the system is on the device.
That is fine. System, what do you mean by system and device?
So this is like systems are complicated. So like signals are going from longer wire or the.
Oh, yes, yes. So, okay, look, for the purposes of this thing, we have some two-port network, okay, which has 2 ports. Inside, it could be anything. It could be long cables, it could be long path lengths. That doesn't matter. What I'm talking about is that whatever response you get for that system is what you are interested in studying. In most practical cases, you will need some cable to connect that system to the network analyzer. This is a small cable, okay? In our experiments, these cables can be meters long. for whatever reason, that's going to give me a huge amount of phase change over frequencies. I'm just trying to remove that trivial. This is just a convenience factor. There's nothing wrong with what we are seeing earlier. You are removing the phase evolution, which is the trivial part, and cancelling it out. So if you overdo this, then you can cancel some of the any phase evolution inside your system as well. So that's why usually I've just connected the cables to the two ends and I'm dialing in a delay time, which is basically telling me how much time it takes. So this number 1.56 is basically tells you that that's the travel time from this end to this end. And the network analyzer has now added an extra negative phase corresponding to that length, that delta t. Yeah, that's why it's able to cancel it over the entire range. No? So what you're dialing is the delta t, and it's multiplying it with omega and subtracting it from the actual phase method.
But I have a range of.
No, that's a
Yes.
velocity.
Velocity is fixed.
So E V by L. L is effective.
So at every frequency, it computes a different number and subtracts it from the measured number. So if you dial in the correct number, you will completely compensate the effect of the cable, which is what you're seeing, that the phase is now flat. Okay, this is now, it looks flat on this scale, but let's look at this in a zoomed in version. So it's not exactly flat. So it's now slightly overcompensated. So let's go. It is close enough for this 1.5595. It's now mostly flat, but the value is around minus 1.8. Phase offset. Now this looks fairly decent. Yeah.
So there was a length there, you know, the entering point. It was
Yes.
activating length is there.
Yeah.
There are many things like ocular axis there.
Yeah, so there are other ways you can enter this. So the method I have chosen is just visually confirming that this is doing the right job. But you could, if you know your coaxial line and its properties in terms of its velocity and stuff, you can enter them directly here. So it's actually saying a velocity factor of 1, which means it's assuming here, I don't remember exactly now, but I think it's assuming that it's traveling at the speed of light, which is why the distance here will probably correspond to 1.59 nanoseconds into speed of light in vacuum. Whereas this actual velocity is not correct, because this is saying this is about, what is this, 500 millimeters, which is 50 centimeters, right? And this is 12 inches. So this is actually not as long as this is expecting, because the speed of light is actually slow in this medium. So that really doesn't matter. What matters is the delta t, which you have dialed down, because delta t is velocity and distance dependent. So that's the number which really determines this thing. So you can enter them in other ways as well. I could have gone into this menu and entered the thing in, because provided I put the velocity factor here correctly. Yeah, it's still all S to 1 only. Okay. See. Okay, good. So just have enough time to finish this part. So all I have done right now is remove this trivial phase evolution from the problem. Okay. So now let's put back the okay. Go back to auto scale. So now after connecting the splitter, it's still showing some phase evolution because now this connector here has not been compensated for. Okay, and there might be some internal lengths as well. So as long as it's just a length of a transmission line, it doesn't matter what we're compensating. So what I will do is now I'll again adjust this to make this as flat as possible. So that looks reasonably good for this purpose. So I've now removed any additional phase path on one of the from going from one port to the other through the device as well. See, if the device had some non-standard behavior, like if it was a resonance, that will not get cancelled out. You would see that on top of this. So there is some, you can see that there is some overall trend which is changing with frequency, which is now a feature of this device's own phase response. But since this is a splitter, we expect it to just have some fixed phase here. So what we want to see now is how does this compare if I now look at the output on the other port. So remember, right now we are measuring S12, which means I'm measuring the output on this side, which is one of the output ports. Let me put this to memory. And I will now shift to the other port, which means S32. So you see there is the overall trend is the same, but there is a slight mismatch in the phase. Now, this would be, the cables are mostly identical, so this cannot be the cable. And even if it was the cable, it would have actually given me a slope rather than a flat offset like this. Okay, so this is something internal to the device. And the point to note here is that the phase difference between the two parts is just a few degrees. So note the scale, right? This is 4 degrees, this is 8 degrees here. So the offset is about 2 degrees. So this is telling you that the two output signals are in phase with each other with an imbalance of about 2 degrees. Okay? This is again a feature which will be specified, or a specification of the instrument will tell you how good is the phase balance as well. Just like how good the amplitude balance is, because you want exactly both of them to be 50% each, but it will not be at all frequencies. So similarly, the phase balance may not be exactly the same. Okay. So this is what is telling you that the two outputs are in phase. The 4-port version of this device, which has the sum and the delta port, will do the exact opposite. If you send in signal through the delta port, the two signals will come out 180 degrees out of phase with each other. Okay. So let me not say too much to confuse things, but the delta port for this device is actually internal to it. You don't have access to it. It's the design of the Wilkinson divider. But this is important to know because this is what will allow this feature to happen. Because these two come out in phase, then they will re-enter in phase. And that's why most of it will come out of the sum port. Because if they are in the same phase, the difference will be close to 0. The sum will be double the value of the individual. Okay. All right. So maybe we have just 5 minutes to show you the other type of splitter. This one is, as I said, it works from DC to 4.2 gigahertz.
Oscillation in magnitude is
Same something, the paths are different. There's like some interference is happening slightly differently at different frequencies. So remember that it's not that the phase itself is changing of one of the signals. What is happening at any port is that multiple signals could be combining with a certain phase relationship, and that phase relationship could change with frequency, which could give rise to the output signal both having an oscillation in magnitude and also in phase, right? It's like basically saying if I combine two sine waves with different amplitude and phases, the output doesn't mean only will have oscillations in amplitude. It can have oscillations in phase as well. So that's what this, again, these are very small variations. This also gives you an idea of typically how accurate microwave devices are when compared to their idealized responses, right? So in microwave office, if you make a Wilkinson divider using ideal transmission lines, it will have a very nice looking response. Then if you make it using the pre-solved models, it will have a slightly worse response. Then if you make it with the actual EM structure and solve it, it will have even more worse response. And then in reality, it will be the worst. Okay. So this is actually the truth of microwave devices. It's not a problem, but that's the level at which you can make these things work. So which is why I was sort of going on and on about these values, because you need to get a sense for when to worry and when not to worry. And this can't really be taught in a class like this. But as long as I flag it to you, you know what you need to do to investigate further. So this is a different type of a splitter, which works all the way down to DC frequencies. That is actually not possible in the Wilkinson divider geometry because of the principle it uses to do the splitting. This is actually more like a voltage divider. When you want to divide a power, what do you do in DC circuits? You do a voltage divider. That's why this one actually works all the way to DC. So let's not worry about the phase for this one. So I'm now measuring transmission. This one is only spec till 4.2 gigahertz. So I'm going to change the stop frequency to 4.2 gigahertz. Okay. And you see that this one has a much flatter response. And the reason for that, it's really just a simple resistor-based network. Okay. But the power is close to -6 dB. This is the price you pay for this kind of a resistive splitter. The previous one, the one which is the Wilkinson divider type model, does not have a resistor except for that difference port, which actually in the ideal case should not even be dissipating any power. Here, because it is using resistors, it's a network which cannot be defined as lossless, right? It's made out of resistors, which is a lossy element. So this is not a lossless network. And this will always have this feature that the output power is going to be 6 dB on both ends, which means it's a factor of 4 in power, and half of the power is lost. So 1/4 goes one port, 1/4. So now let's put this to memory and look at the other one. So that is going to be S32. So mostly the same, again, slight shift in these frequency patterns, but it's also -6 dB. So remember, 3 dB is factor of 2, 6 dB is another factor of 2, factor of 4. So 1/4 comes out of one port, 1/4 comes out of the other port, and the rest of the 1/2 dissipates inside the device itself.
Is there a particular reason why it's so flat?
Yes, because it is easier to make a resistor have the same response, right? So in fact, I have not shown you the circuit for this. Maybe in the next class, I will, when we study the splitters, I will show you. It's just a resistive network divider. And it's a lot easier to make them to have a flat frequency response. However, not so easy to make them flat over arbitrarily large frequencies. That's why this particular device, so this is a low cost version of these things. So up to 4.2 gigahertz, it looks fine. But if I look at it after that, it's start increasing loss. Anyway, you can't really make sense out of these numbers because it depends on how the resistor is made and other things. Whereas the Wilkinson divider relies on some kind of an interference phenomena for it to work. So it depends on reflections, it depends on the length of the transmission lines used in the network. And that one can have an ideal frequency response of operation, and then it will deviate after that. Okay. So these have different applications. If you really need a flat response and you need to work all the way down to DC, then you have to use a resistive network. There are, costlier versions of this which will give you this resistive splitter working up to 10 gigahertz and 20 gigahertz or so. But otherwise, we can look at the other parameters. Let's look at reflection on port 1. Okay, so again, fairly low reflection. Let me stop the frequency at 4.2 gigahertz. So you see, it's almost everything is below minus 20 dB. So it's very nice in that sense. Let's look at S33, which is the other port. That also looks quite good. And we can look at the source port as well, which is S22. So all three ports are also well matched. So again, it's a matched device on all three. And it's also a reciprocal device. So the lossy part doesn't make it non-reciprocal. So S21 is the same as S12. In fact, here they are quite well mapped. Similarly, if I look at SP2, put that to memory, and compare that with S23, same. So it's again a passive network. Only difference from the previous one is that this one is by design not lossless. The other one by design is supposed to be lossless, but in practice, because of finite conductivity and other things, it's going to be slightly lossy. But this one loses almost 50% power inside the system. And finally, we look at the phase. So that memory. This was S23, so we have the other one is S12. So again, the two outputs are in phase even for the resistive splitter, which is what it's supposed to be. Okay, so let's stop there. Are there any quick questions I can answer? Can you do what? Yeah. No. So the question you have to ask is not whether a voltage divider works at high frequency or not. A voltage divider is just a circuit involving multiple resistors. So the relationship between input voltage and output voltage will be the same at any frequencies. The question you have to ask is that when you make it, is the resistor you're designing remains a resistor at all frequencies or not? That is what's going to change. You will make the resistor using some material. It will have some finite size, which means it's going to have some capacitance to ground. It might have some inductance. These things might be irrelevant at very low frequencies, but they will be relevant at high frequencies. So that's why the difference between, I said, expensive versus cheap instrument or device, that's what they do. Like this one, which is the low cost version of a resistive splitter, probably has a material choice for the resistor, where the material, we know that that material is going to be frequency dependent versus something which is not frequency dependent. So that changes the cost. It also changes the packaging you have to make. So if you have to make things work at very high frequencies, you have to make things usually smaller and compact. The connections have to be as short as possible. So that's what determines whether it remains to be the circuit you have drawn. But a voltage divider is a voltage divider, right? It doesn't depend on whether it's an AC signal at the input or not.
The resistance is dependent on the
That basically what I'm saying, that depends on the type of material you use to construct that resistance. It's not just that the resistance itself will change. That just means that it's a different voltage divider still composed of resistive components. The thing which typically happens at high frequencies is that your resistor will no longer remain a pure resistor. It will be some impedance. It will have some capacitance to it, some inductance to it. So it will now develop other kinds of frequency responses, which basically cannot be explained by a simple resistor model. That's what happens when you go to high frequencies. So there are standard method tricks like, small size, choose the right resistance material. Usually for high frequency circuits, they will use a nichrome alloy, which can give you a lot of resistance in a very small package. So you can buy surface mount resistors, right? They also come in different sizes. It can be this big or it can be very, very tiny. So the general rule of thumb is that if it's smaller, it will work to higher frequencies. But then it has to be also packaged correctly, because you cannot have a voltage divider network on a breadboard or a printed circuit board and you have wires sticking to it, right? You need some transmission line to feed the signal. Then that transmission line on chip has to connect to some connector like these things. Okay. So when we look at study these devices in detail, I will also open one of these devices and show you how this packaging is done, how you transform signal from a coaxial geometry to a planar geometry. I had passed around some boards in one of the earlier classes, right? So those things also determine whether it will work well at high frequencies or not. So that means that not only the resistors you have made, the printed circuit board you use, the type of transmission line you use, the type of connectors we use, the type of transition from one connector to the other, all of these things determine whether something will work at high frequencies or not. So that's what changes the cost of the device itself. Well, it depends. If your application does not require going down to very low frequencies, then the Wilkinson divider is a better choice because you will not lose power. But if you don't care about losing that power because you have enough power to source with, then you can use a resistive divider as well. These are all very application dependent. It could also depend on the conditions. So, for example, in our lab, we do experiments at cryogenic temperatures. Now, if I'm going to use a lot of power and I want to split it, I would ideally not like to dissipate that energy at low temperatures because that can cause heating. So I would try to avoid unwanted dissipation in my system. So I will use a Wilkinson divider. But there are some applications where you might need both DC and RF to be going in the same path. So then you cannot use a Wilkinson divider because that will not allow DC to go through. So very dependent on what you're trying. Okay. All right. Let's stop there.